recording. And then I'm going to start to share screen, the usual routine here. Let's see here, let me get it bigger. Let me lock it in place if I can. Let me turn my light, which may help for later. It doesn't wash out. As it gets dark, it'll be better. I spent some time this afternoon trying to see if I could rotate this thing, which would give me more real estate on the screen. But apparently Zoom doesn't let me do that, so I'm not too happy about it. All right, to get started tonight, I've got a review page here, some of the things we did, not so much to review tonight. Some of our main accomplishments were to work out the various Fourier series representations of the fields, the vector potential, the electric field, and the magnetic field. I'll remind you that here we're just working with the free field. And in the case of the free field, the electric field is purely transverse, so the little perp index in there is really not necessary for that case. But in the case here of the Fourier series, and I'll remind you that I'm using lambda here as a mode index, which is a compound index. It consists of a k vector, which has to lie on a lattice point in k space, and a polarization index that only runs over 1 and 2. That's the two polarization vectors that are orthogonal to k. And this is a little bit too bright. I think I'm going to try to tone down the light a little bit to see if it'll work a little better, be a little less bright. And I think that's better. Is that better? Yeah, I think so. All right. These started out as Fourier series in the classical field, in which case the A and A star were what we called normal variables, are basically proportional to the mode amplitudes. But when we quantize them, they become A's and A daggers, and they're creation and annihilation operators for the corresponding harmonic oscillators. This makes the fields themselves into quantum fields parameterized by the position x, the operators parameterized by x. We worked out these fields. We also worked out the Hamiltonian for the free field. This is all with box normalization on this page. And it's a sum of basically the photon energy multiplied by the number operator. That's the Hamiltonian. This can also be written as the integral over space of the divided by 8 pi of the b squared plus b squared, which would be the classical expression for the energy density in the electromagnetic field, except here we use the quantized fields, which are given just a few lines above, up here E and B, and we normal order it by putting colons around it, which makes vacuum expectation values vanish. If you do that, then you find the answer is given as given here on the left, without a 0-point energy. Similarly, for the momentum, we use a normal ordered version of what would be the classical expression for the total momentum of the field. This is linear momentum now, linear momentum of the field, free field only, but it has to be normal ordered in order to make vacuum expectation values vanish. And if you do, you get basically the sum over modes, the number operator of the mode. That's what this A lambda dagger A lambda is, multiplied by the momentum in a single photon. All right, so I think that's a review of what we've done. Are there any questions about that before we proceed? All right, if not, then the first topic for tonight is statistical mechanics. We do this partly because it's easy and it fits in well at this point in the development. The basic idea here is that we want to set up a box of radiation. The box is empty except for electromagnetic field that's inside of it. But we hold the walls of the box at a temperature T. It wouldn't have to be the whole wall, even just a part of it would do, in order to place the radiation inside the cavity into contact with a heat reservoir at a given temperature. And anyway, that's the setup. Now, in doing equilibrium stat mech, of course, we're interested in the partition function. And in a general notation, it's the sum over the energy eigenstates n times e to the minus beta E sub n, where the beta is the usual thermodynamic parameter 1 over kT, or k is the Boltzmann constant. For this application, the label of the energy eigenstates needs to be replaced by an infinite string of occupation numbers, because we'll use the occupation number basis here for the labeling the energy eigenstates. And likewise, the E sub n has to be replaced by the energy of the basis state in the occupation number basis. And that's a sum over modes lambda of n sub lambda times h bar omega lambda, the number of photons in a given mode multiplied by the energy of a single photon in the mode summed over modes. And if we do that, then the partition function, just by change of notation, turns into the sum over all possible strings of occupation number integers. That's quite a large and infinite sum of e to the minus beta times the sum on lambda of n sub lambda h bar omega lambda, like so. Now, the exponential of a sum like this can be written as a product of exponentials. So I can write that as a product over modes lambda of e to the minus beta n lambda h bar omega lambda, like so. And now what we have is a sum over products in which the indices run over all possible combinations of indices. The sum of products of this form can be rewritten as a product of sums. And in this case, it turns into a product over the modes lambda. And the sum in question is a sum where n lambda runs from 1 to infinity of e to the minus beta n lambda h bar omega lambda. Omega depends on lambda because lambda contains k, and omega depends on, of course, omega does not depend on the polarization. It just depends on the k part of lambda. In any case, this in lambda sum is now a geometrical series and can be summed. So this turns into the product over lambda of the sum, which is 1 minus e to the minus beta h bar omega lambda, like so. And that's the partition function for the free electromagnetic field contained in a box. Now, once we've got that, we can start to compute the various thermodynamic quantities. For example, the energy is minus the derivative with respect to the beta parameter of the logarithm of the partition function. And that's the derivative with respect to beta of the sum on lambda of the log of 1 minus e to the minus beta h bar omega lambda, h bar omega sub lambda, like so. And then carrying out the derivative, just using the chain rule, we get the sum on lambda. We get a denominator, which is 1 minus e to the minus beta h bar omega lambda. In the numerator, we get e to the minus beta h bar omega lambda, just using the chain rule. And this is then multiplied by h bar omega lambda, like so. So that's the energy in the thermodynamic sense. It really means the average energy, if you will, over the ensemble. Okay, which here is the canonical ensemble. Now you see this energy then is now written as a sum over modes times the energy of a single photon in that mode times the dimensionless number. And that dimensionless number therefore has to be interpreted as the average number of photons in the mode. I'll call it average value of n lambda. Because if you do, you get a rather obvious expression. It's a sum on lambda of the average number of photons in that mode multiplied by the energy of a single photon. And so this derivation, and it gives us an expression for the average number of photons in mode lambda. And if I can clean this up a little bit by multiplying numerator and denominator by the quantity e to the plus beta h bar omega lambda. And so this gives me 1 divided by e to the beta h bar omega lambda minus 1. And this is one of the simpler ways of expressing the Planck spectrum. It's a formula I expect you've seen before, especially now that you're all taking 211. He's probably done it by now. Anyway, so that's the derivation. Now, the main thing I want to say about this derivation is just to point out how easy it is. We are dealing with an infinite number of harmonic oscillators, but except for that, it's just each one of them it's just a repetition of simple operations that you do on a single harmonic oscillator in thermal equilibrium with a heat bath. And this is just a combination of those because running over all the modes. And in particular, all we rely on here is the basic Boltzmann hypothesis that the probability of being in a given energy state is proportional to e to the minus beta E sub n, so that Z is the normalization of that probability distribution, which then serves a role as a generating function of the various thermodynamic quantities, such as here is the energy of the system. So there's no special assumptions that are required to deal with the thermodynamics of the field. We just use Boltzmann's old hypothesis and nothing else for equilibrium stat mech. That's all. This result can be leads to other closely related results that I want to mention briefly. One of them is that in this sum here over lambda here, let me rewrite this sum in a slightly different way. As a sum on lambda of, I'll put the h bar omega lambda on top, and then we'll have e to the minus beta h bar omega, e to the plus beta h bar omega lambda minus 1 in the numerator. So that's the expectation value of the energy. This sum on lambda, if we take the volume of the box to be large, the sum on lambda can be replaced by, well, in any case, it can be replaced by a sum on k, which runs over the lattice points in k space, and a sum on mu, which runs over the two polarizations. If we do that, the sum on mu gets replaced by just 2 because the thing we're summing doesn't depend on polarization. There's only 2 polarizations. And as far as the sum on k is concerned, we can, in the large volume limit, turn that into an integral by writing it as v over 2 pi cubed times the 2 pi cubed times the integral over k space, d cubed k, like so. Let me make some more room here for see how that fits. And then that in turn, the integral d cubed k, we can do the angular integral because the integrand up here doesn't depend on the direction of k, so we just get a 4 pi. And then what's left over is integral 0 to infinity of k squared dk. And if we switch to omega as a variable of integration, that becomes omega squared d omega divided by c cubed. And so putting all of this together, we get the energy of the field then is equal to, actually, let's write it this way. Let's divide by the volume. That gets rid of the volume factor, which came there from the density of states. Let's get the energy is proportional to the volume, which you would expect. So let's take E over V and define this as U, which is the energy density. And then that's just basically given by following this chain of stuff back and getting the coefficients right. And so it's going to be volume over 2 pi cubed times 2 for the polarizations times 4 pi for the solid angle. And then we've got the h bar omega in there. There's an h bar that comes out. And then there's an integral 0 to infinity d omega of omega cubed divided by e to the minus beta h bar omega, e to the plus beta h bar omega minus 1. That integral like that. And I should have left this volume out because I divided by the volume. It's just 1 over 2 pi cubed here. All right, so we can clean this up. This factor here is going to be, oh, there's a 1 over c cubed that came in here too. I have a c cubed in the denominator here. So this factor turns into h bar over pi c cubed, like so, if I did that right. So if we write this in as u then is equal to the integral from 0 to infinity of d omega of the quantity I'll call du d omega, where du d omega is the energy density per unit frequency interval, then we get an expression for du d omega, and this is the usual way of writing the Planck formula. It's h bar divided by pi c cubed times omega cubed divided by e to the beta h bar omega minus 1. And I'll box that because this is the accomplishment of Planck, is to derive that formula. But it's just really closely related to the expectation value of n lambda we saw above when you take into account density of states and do the integral and so on. By the way, I didn't actually do the integral. If you do the integral, you get u itself. And the answer turns out to be pi squared over 15 times kt to the 4th power divided by h bar c cubed. Let me box that too, because that's also an important result. In fact, of these two boxes here, the du d omega gives the distribution of energy over frequencies, and the lower box here is just what you get when you integrate that over all frequencies, just to get the total energy density at all frequencies. A little bit of history here is that well, first of all, the formula giving U itself is notably proportional to the fourth power of the temperature. This is related to the Stefan Boltzmann law. Stefan Boltzmann, and it was derived or made its first appearance in the 1870s. I don't know who gets credit for doing it first, but Stefan was an experimentalist and Boltzmann was a theorist. And the theory that Boltzmann used to derive this was that he used classical thermodynamics, and he took black body radiation as a working fluid in a Carnot cycle, and carried out a Gedanken experiment in which he compressed it and then did adiabatic expansions and compressions and so on, running it through a cycle, and was able to derive this expression for the energy density. He also got an expression for the pressure and therefore the equation of state of the black body radiation. It's a fairly simple calculation. You could easily do it at the undergraduate level. It's quite interesting. It uses a small amount of electromagnetic theory. And it's strictly classical, as a matter of fact. But Boltzmann was not able to find out how the energy was distributed in frequency. And that was, of course, Planck's great accomplishment. It was a much more difficult job. Planck worked on this for at least 10 years before he got the final answer. And he probably wouldn't have been able to get that answer without getting some good experimental data on the distribution over frequencies. All right, anyway, the fact that the energy density goes as the fourth power of temperature, of course, means that you get a lot of energy density. Energy density increases rapidly with temperature. So the T to the fourth dependence is probably the most notable aspect of that formula. It means that things that are very hot radiate by black body radiation really a lot, much more than they do at lower temperatures. So things cool off pretty quickly if they're at any elevated temperature. So for example, when a nuclear bomb explodes, the nuclear reactions take place over a very short period of time and create a localized region of space with extremely hot material, maybe millions of degrees. But because of this T to the fourth dependence, it starts to radiate extremely rapidly, loses heat very rapidly. And that heat is going off in the form of X-rays because of the high temperature. If the bomb is in the atmosphere, the X-rays don't actually travel very far because they're absorbed by the air, more or less at the speed of light. And so what you get is a shell of air surrounding the original explosion quite rapidly, very rapidly, which is raised to a very high temperature, but still not as high as the temperature of the original explosion. Anyway, the explosion dynamics is governed then by the progressively lowering temperature black body radiation as the fireball gets bigger. And at a certain point, the temperature is low enough that most of the energy is coming off in the form of visible light or ultraviolet light, which has a long range in the atmosphere and travels for a considerable distance. Anyway, evil applications like that are the kinds of things you think about when you see the T to the fourth here. All right. Anyway, that's a bit of the story of black body radiation involving the quantized electromagnetic field. Once you understand how to do it, it's an easy calculation. Although historically it was hard. I mean, it represented the birth of quantum mechanics in 1900, but it was 25 years after that before anybody understood exactly how to do the honest statistical mechanics of it. All right. Anyway. So that's a little bit of equilibrium stat mech of the electromagnetic field. Are there any questions about that before I go on to the next topic? By the way, to make a slightly more benign application of the T to the fourth power law, in stars, the sun is not amongst the larger stars. It's reasonably big, but in the sun, the pressure which holds the star together against the force of gravity is provided mostly by the matter. It's just mostly the 3/2 kT that you well, that's the energy. The pressure is different, but it's the ideal gas, mostly ideal gas pressure law, which provides the pressure. But in stars with a higher temperature, because of this T to the fourth dependence, it's actually the photons supplies most of the pressure that holds the star together. All right, so anyway, all right, so that's all some aspects of that. Next topic I'd like to take up is that of the Heisenberg equations of motion. Let me get some of these papers out of the way here, and bring back. I want to bring back my. I want to bring back my mode expansions of the field. This is the summary that we started with at the beginning of the hour tonight. Let me bring it up here, put it in place. So we have the fields here, A, E, and B. And without saying it, the interpretation that I've been following in presenting this material is a Schrodinger picture, the usual one we use in quantum mechanics. So the operators are independent of time and the state vectors evolve. But of course, we can flip it around and consider that the operators evolve and the state vectors don't. And it's worthwhile looking at what happens if we do that. Let me begin some of the calculation down here because I have some room. For example, if I took the electric field, and I'll leave the perp off of this because this is understood to be the free field only. If I take the electric field and it's parameterized by x, it's a definite observable at a definite position x, and I wish to compute its time derivative a la Heisenberg, that's 1 over IH bar of the commutator of the electric field E of x with the Hamiltonian, like so. And if I write this out schematically, there's 1 over IH bar. The electric field is a sum over modes lambda. I won't copy the whole thing here, but the essence of it is that it's got an annihilation operator in one term and then a creation operator in another term. So there's an A lambda there, and then there's an A lambda dagger with a bunch of other constants and stuff that are in there. And then we form the commutator of that with a Hamiltonian. So let's look at the commutator of the A lambda with the Hamiltonian. A lambda with a Hamiltonian commutator is going to be writing out the Hamiltonian. It's going to be the sum on lambda prime of h bar omega prime times the commutator of A lambda with A lambda prime dagger A lambda prime. I'm using the lambda prime sum for the Hamiltonian. You see it's up here given as a lambda sum, but I don't want to confuse it with the lambda index that's used in the expansion of electric field. Anyway, using the rules of harmonic oscillators, harmonic oscillator creation and annihilation operators, basically just the commutation relations, it's quite straightforward to work out this commutator. And if you do, what you find is that it's h bar omega sub lambda multiplied by A lambda. And likewise, the commutator of A lambda dagger with the Hamiltonian gives you the same thing, similar thing, except with a minus sign. It's minus h bar omega lambda multiplied times A lambda dagger, like A lambda, not A lambda prime, A lambda dagger. You get these two commutators. And so we can take these commutators and we can put them into here and into there and do the sum over E. And it's completely straightforward to do that. And I'll let you look at it yourself to fill in the details. It's hardly an exercise. It's very short, just glancing at what you're doing here. But when you do that, what you find is that the time derivative of the electric field, a la Heisenberg, can be written as speed of light times the curl of the magnetic field, where the magnetic field is understood to be its own Fourier series up here. Likewise, if we compute the time derivative of the magnetic field, using, again, the Heisenberg equations of motion, we get it with a minus sign, C times del cross E. And these, in fact, are Maxwell's equations in vacuum for the electric and magnetic fields. Maxwell's equations are not all time dependent. There's also some time independent versions of them. They're the divergence equations, del dot B and del dot E are both equal to 0 for the vacuum field. And these also follow as operator equations by taking divergences of the series that we have up above. And so the main conclusion of this is that the Heisenberg equations of motion are valid the Heisenberg equations of motion imply a version of Maxwell's equations. Maxwell's equations are valid in quantum electrodynamics, except they're interpreted as the Heisenberg equations of motion for the operators, the quantum field operators, rather than for the classical fields. If we included matter, we'd find that it was true even with the matter driving terms, the currents and so on. They'd be true in that sense as well, now with quantized matter. All right, so that's a bit about Heisenberg equations of motion. The next topic I want to address is that of getting rid of boxes. Let me get half a piece of paper here. Basically, I want to look at the limit that the volume goes to infinity. There's several reasons for doing that. Probably the most important is that boxes are non-physical. Also, there are certain topics that are difficult to handle in box formalism, such as the angular momentum of the photon is a somewhat complicated subject, but boxes makes it worse because the angular momentum, is the generator of rotations, and boxes are not invariant under rotation, so they kind of destroy the rotational symmetry if you try to use them. So anyway, I'll remind you here, I've summarized this, of the rules that we had for taking the limit where v goes to infinity. These are basically rules that turn our Fourier series for box normalization into Fourier integrals. The sum on k turns into the density of states v over 2 pi cubed in k space times an integral in k. The number of lattice points, density goes to infinity as the volume of the box goes to infinity. So this is the substitution you need to make. If you take the expression for the Fourier series coefficient of let's say a scalar field, call it S sub k, then you need to make this change. You need to scale it by these factors that are given here, including a square root of volume, in order to produce what in the end is going to turn out to be the Fourier transform. This is using our conventions for Fourier transforms about the positionings of the factors of 2 pi. But with those conventions, this is the rule we want to use. Also, the Kronecker delta, which is, after all, a Kronecker delta when you have lattice points in k space, because either they're equal or they're not equal, goes over in the limit into, again, there's a factor involving 2 pi's in volumes times a Dirac delta function when you replace sums by integrals. This is the correct changes to make. So these are the rules. They're easy enough to work out if you just write down the Fourier series and see what is needed to convert them into Fourier integrals. But let's now apply them to the Fourier series, which I'll bring back yet once again, which we worked out in the previous lecture for these various fields, the vector potential, electric and magnetic fields. These are all Fourier series. This lambda involves a sum on both k and on mu, but in particular, it's a sum on k. So these are Fourier series. So one of the things we want to do is to treat the creation and annihilation operators, which appear here, as if they were Fourier coefficients of a Fourier series of A. I mean, they're proportional to that. So let's treat them in the same way that we would the coefficients of a numerical Fourier series, except now these are operators. In any case, here's the changes we want to make. I'll summarize them for you here on another page. We want to make the following changes. First of all, let's talk about the polarization vectors, because that's a simple change. We have epsilon lambda, which is the same thing as epsilon hat k mu, because that's what lambda means. Let's set this equal to epsilon hat sub mu of k, which really means the same thing. It's still the same polarization vector. They're just two unit vectors that span the perpendicular plane. But I'll write it in this form if I want to remind ourselves that k is a continuous variable rather than a discrete variable, rather than this notation here. As far as the A lambdas, the annihilation operators, which are also A k mu, we'll replace these by 2 pi to the 3 halves divided by square root of volume v times what I'll call A sub mu of k, where, in other words, this is now in effect a continuum version of the annihilation operator. And we'll do something similar for the creation operator A mu dagger of k. It'll be related to its discrete version by the same prefactor and the same type of formula. All right. Now, if we make those changes, then the Fourier series that I've written down turn into Fourier integrals. I'll get to that in a minute. But before we do, I want to say something about the creation and annihilation operators. The creation annihilation operators in the box normalization satisfy commutation relations that look like this. If I take an AK mu and an AK prime mu prime dagger and compute those commutators, all commutators of A's with A's or A daggers with A daggers are zero. The commutators of an A with an A dagger is non-zero, and it's a Kronecker delta in both the K and also the KK prime Kronecker delta, and also a mu mu prime Kronecker delta. It's a Kronecker delta in both of those discrete indices. Now, on the other hand, if I go over to the continuous version of the A's and A daggers, using the rules I just summarized, then the commutator becomes this. It becomes A mu of K vector, commutator with A mu prime of K vector prime, dagger. That's still a Kronecker delta in the polarization index, delta mu mu prime, but it becomes a Dirac delta function in the wave vectors, K minus K prime. Turns into a kind of a continuum sort of a thing like this, as you would expect, because you're going to get a continuum when the box goes to infinity. Now, the fact that there's a square root of volume here and this factor here is an indication that these operators A mu of K are actually by themselves not physical. In the box, the A lambda or AK mu was physical, or the dagger version of it was. Certainly, they're both physical operators. For example, the dagger version of it is I didn't write it down here, but the dagger version of it is the operator that acts on the vacuum and puts one photon in the mode. And if you've got a box of finite volume, putting one photon in the mode makes physical sense because you've got a finite amount of energy in a finite volume. But when you go to infinite space with no boxes, you can't have one photon, not in a plane wave anyway, not in a momentum eigenstate, because it fills up all of space. And so it's like the density of energy, it goes to zero. So it's a non-physical limit, and it's the sort of thing that it doesn't make any sense physically. In fact, the situation is very similar to what we do with wave functions of ordinary massive particles when we compare wave functions in a box. Let me just mention that. If I were dealing with a massive particle, which we've been doing, by the way, in recent lectures, if I have, let's say, psi k of x in a box like this, and I want to normalize it to the box, it's 1 over the root volume of the box e to the ik dot x. And then k has to be quantized, and this obeys discrete. These are normalizable states, you see, normalizable because of the integrator over the volume of the box. But in the limit that we go to infinity, we have box goes to infinity, we use different wave functions, psi k of x, which we also wrote this way as x scalar product with k vector. And this is equal to e to the ik dot x divided by 2 pi cubed. It's actually 2 pi to the 3 halves to do it right. It's 2 pi to the 3 halves. And this has the property that the scalar product with k prime is a delta function in k. But this wave function no longer represents the state of a physical particle because its norm is infinite. It's not normalizable. Real wave functions are normalizable, and this one is not. We made a compromise here. We spread the wave, we got an a momentum eigenstate and spread the wave function over all of space. But as we did that, we increased it, we allowed the wave function to be not normalized. And we kept increasing the wave function as we spread it over further and further regions of space so that it stayed a finite value in the end. And so the result is we end up with something that's not normalizable and therefore non-physical. So the action of these A mu of Ks, so this is the idea, is that the AK mu acting on the vacuum, dagger acting in the vacuum, is like this. It's like this normalizable particle in a box wave function, whereas A sub mu of K, dagger acting on the vacuum, is like one of these plane waves that fills up all of space. And that means that we get physical results not by letting one of these A daggers act on the vacuum, but we need to integrate over K with some weighting factors to create, if you will, wave packets and normalizable states. And I'll come back to that a little later, but that's the idea here. In any case, if I make those changes, then the quantum fields, the boxes go away, the volumes of the box go away. The changes are mostly pretty elementary, but here's a summary of what you get for the three fields. I'll just show you how it goes for the vector potential. It's more or less the same prefactor as before, except there's no volume anymore. All the volume factors cancel if you do this. We get, instead of a sum on K, we get an integral, and the 2 pi 3/2 is our standard convention here for Fourier transforms. There's a sum over polarizations. Combination of this integral and the sum is what we call sum on lambda in the discrete case. And the rest of it is pretty much looks the same as what we had before. There's a polarization vector, which really hasn't changed except for notation. There's the annihilation operator, which has changed by this normalization, same phase factor. Okay. And it's similar also for the E and B fields here. So these are the quantum fields we have in the case of when we get rid of the box and we go over the continuum. In a similar manner, we can take the Hamiltonian for the system, which was a sum over modes, as you'll recall, number operator times h bar omega. And when we go over the continuum limit, we now get an integral like this, integral over K, sum over polarizations. There's the photon energy in the mode. And you get an A dagger A, which is, you'd be tempted to call it a number operator, except these A's, remember, have been scaled, so they're kind of not normalized anymore. But that's the idea. Anyway, this is still equal to the integral over all space of the normal ordered E squared plus B squared. If I use the E squared and B squared up above here and do the normal ordering, you can go through the integral and you can prove that this is equal to that. So this is now the version of the harmonic oscillator, excuse me, of the Hamiltonian for the free field. It involves a kind of an integral over a continuous distribution of harmonic oscillators. And this is the reason why I introduced the box normalization back at the beginning, because continuous distributions of harmonic oscillators are not what we're most familiar with in classical mechanics. So this was a route to get to the more physical answer in as painless way as possible. By the way, also the momentum of the field, we did this one too, is now also represented by a similar kind of integral and sum. It's h bar k, and again there's an A dagger A. And this is again equal to the normal ordered version of E cross B, where E and B are now the quantum fields, not the classical fields, although this formula is borrowed from classical theory. And the colons mean normal ordering. Right. Now, before I leave this subject, I want to derive what I'll call a useful matrix element. And here's what it is. It's a vacuum expectation value of A mu of K vector, an annihilation operator, times an A mu prime of K prime dagger, and then close the vacuum expectation value. This is a useful matrix element. I'll remind you that if you have an annihilation operator next to the vacuum ket, the answer is 0. Likewise, if you have a creation operator against the vacuum bra, that answer is 0 also. But that's not what we have here. We have the dagger against the ket and the annihilation operator against the bra. So this matrix element is non-zero. We'd like to evaluate what it is because it comes up several times. The way to do it is to use the commutation relations between these two operators. If I reverse the order, I get A mu prime dagger of K prime times A mu of K, like this. And then I add the commutator to it, which is Kronecker delta mu mu prime, direct delta function of K minus K prime. And what you see is the first term vanishes because now we do have an annihilation operator, namely this one, adjacent to the vacuum ket. And so this term goes away, and all that's left is the commutator, which is a C number. So the C number is sandwiched between the vacuum, but the vacuum scalar product with itself is 1. Vacuum is normalized state. So we just get the commutator. And I've summarized this over here on this page with a useful matrix element. And here it is. There's exactly the matrix element I just wrote down. And here's the answer. It's just these Kronecker delta times Dirac delta function. We'll see this thing coming up in applications of this in just a moment. All right, so those are some aspects of taking the volume goes to infinity limit.
I have a question.
Yes.
Why is it a given that the vacuum state is still normalizable now that we've taken this limit?
Well, it's we didn't change the vacuum state. I mean, if you think about the limit in terms of letting the volume of the box goes to infinity, the vacuum state doesn't change. I mean, it's the ground state of the system. Okay, I mean, these states that I'm getting by letting these continuous versions of A act on the vacuum, they can be regarded as limits of what you'd get by applying a discrete A to the vacuum, but then multiplied by that scale factor. But the trouble is that limit leads to if you don't take that limit, you're going to get zero density. And well, excuse me, if you don't take that limit, the wave function goes to zero, in space. Also, you also have the energy density goes to zero in space too, because you're putting just one photon of energy h bar omega in a box and letting the box get bigger and bigger. But none of that none of that has any impact on the normalizability of the vacuum state. Maybe my answer is not too good, but that's the best I can say about it right now. This is the logical way of doing it. All right, come to office hours and we can talk about it some more if you want. All right, so the next thing that I want to talk about is measurements of the field quantities. Let me go back to my summary here. Summary sheet. And here are the Fourier series again. This is in continuum form, the ones we just worked out. Let's look at the electric field. Again, E perp is really the same as E because it's still the free field. So the electric field is an observable. It's something you can actually observe, but you have to choose a place to observe it first, and that's what the X is. The X is not an observable. It's just a parameter of the observable. And of course, by the postulates of quantum mechanics, observables are associated with operators. So this is an operator valued field, i.e. a quantum field. That's just what I've been saying the last several lectures. Now then, what this means is that measurements of the electric field, since we're doing quantum mechanics, are presumably subject to the usual things that happen in quantum mechanics. That is, for example, when we make measurements on an ensemble of identically prepared systems, we don't get the same answers. Instead, we get a statistical distribution of answers. And so this raises the question of what is that statistical distribution depending on the state in question. The simplest state to look at is, of course, the vacuum state, and that's what we're going to look at in just a second. By the way, the quantum mechanics also tells us that we should have various types of uncertainty principles and relations connecting, in this case, the electric field to other operators that don't commute with the electric field, generalized uncertainty relations, and this is also true. So it turns out it's impossible to measure both the electric and magnetic field with simultaneously with infinite precision because they don't commute with each other. But let's just focus for now on the measurement of the electric field. All right, and let's take the state in question to be the vacuum. So let's talk about that. So here, let me separate this off because I'm done with that. So what we want is electric field at a spatial point X like this. And we would like to let it act on the vacuum. Let's initially look at the vacuum expectation value, the expectation value of the electric field evaluated at a point. That's the first statistic to look at. The electric field is a rather complicated series, but it involves integrals and sums. But basically, what you're integrating and summing is you've got A's and A daggers. They would be K mu like this. I'll leave that off. But anyway, that's what the electric field is. It's a sum of that type. And the first term with the annihilation operator, and it gives us an annihilation operator here, which is adjacent to the vacuum ket. And so that goes out. The creation operator in the second term is adjacent to the vacuum bra, and so that goes out as well. And so it's fairly easy to see that the average value of the electric field measured in the vacuum is equal to 0. Well, this is what you'd expect physically. If there's nothing in the field and you go out and you measure the electric field, you ought to get an average of 0, right? But quantum mechanics says that maybe there's fluctuations around this and that only the average is 0, but not the actual measurements that you get. Is that true? Well, the way to find out is to compute the dispersion. So let's do that. Let's look at the dispersion. Let's look at E of x vector squared, and we'll take its vacuum expectation value and see what that is. So the way to do that is I'll bring back my paper here so you can look at the series. I've got 2 copies of electric field. It's basically E dotted into itself. That's what E squared is. So here's the integral for a single copy of E. I want to write this down twice to get 2 copies of E. I want to take one of these and prime the dummy indices K and mu, prime them. I want to, and then I want to multiply those 2 series together to get the E squared, which is going to be inside the matrix element. So if you can kind of see what's going on here, I've got a square root of 2 pi h bar integral sum square root of omega and then this stuff. So let's run through it and see what we get. So this is going to give us, first of all, a 2 pi h bar from the square of the prefactor. There's going to be a double integral on k and k prime. And it's going to get divided by 2 pi cubed because that's 2 pi 3/2 squared. There's going to be a sum on polarizations mu prime. To go back here to the E, there's a square root of omega there, except there's going to be 2 of them. So I have the square root of omega prime. That's going to be a factor that's in there. And then I need to multiply this by the rest of it. And here I better put in the vacuum bra because I need that here, you see. And then I'm going to get what's left of the first factor of electric field. I'll write this as I epsilon sub mu hat of k vector times a sub mu of k times e to the I k dot x. And then I'll put in plus Hermitian conjugate. And then that gets dotted with, I'll write it as Hermitian conjugate minus I epsilon sub mu of k vector star times a mu of k vector dagger times e to the minus I k dot x, like that. And I better go through here and put primes on the mu's and the k's because this is the second sum. And then I need the vacuum bra over there on the right. All right, and so this ran off the screen a little bit, but there you go. That's writing out the whole thing in some detail. Now, in this first Hermitian conjugate, which is here, we have an annihilation operator, and that's actually adjacent to the vacuum bra, and so that term goes out, that dies. Over here, I have in the second Hermitian conjugate, this contains an annihilation operator, and that's adjacent to the vacuum ket. And so this term dies also. And so it's only the terms that I wrote out explicitly. Of the 4 terms you get by multiplying these together, there's only this one cross term that's going to give you a non-zero answer. Now, most of the stuff you see in these terms are C numbers, where the operators are really just the A mu here and the A mu dagger there. And this is sandwiched between the vacuum 0, 0 and the 2 sides. So if I just collect that part together, I get a vacuum on the left, I get an A mu of K operator, and then I get an A mu prime of K prime dagger operator and a 0 on the right. This is the essence of the matrix element part of that integrand. But this is the useful matrix element that we worked out just a little while ago, and it turns into Kronecker deltas and Dirac delta functions. So that's what this gives. It gives me delta mu prime and delta of k minus k prime. And so obviously what this is going to do is to allow us to do the not only the k prime, we'll be ending up setting k equals k prime, and therefore omega equals omega prime, and we'll set mu equals mu prime. Just drop the primes basically, and that will get rid of also the k prime integral. We'll get rid of the mu prime sum. And I'm doing this in red, so I hope you can see that. And so if you clean this up, then this expectation value that we started up with here of E squared, what does it turn into? Simplifies a lot. We got a 2 pi h bar still there. we get an integral over k, d cubed k. This is now divided by 2 pi cubed, because that's still there. We get a sum on mu, now a single sum on mu. The omega, root omega omega prime just turns into a single omega because the two omegas are equal. And then multiplying these factors together, I times minus I is 1. There's the dot product of the polarization vectors. It's epsilon hat sub mu of k dotted into epsilon hat sub mu of k complex conjugated. These were originally prime, but we dropped the primes, remember? And then the A's and A daggers we took care of because that was a matrix element. And then all that's left are the phase factors, but when k is equal to k prime, the phase factors cancel too. So this is all we get down at the bottom. That's what's left. Simplified a lot. Let me tear this page off so I can get more room. It's simplified a lot. This dot product of polarization vectors is equal to 1 because it's just a polarization vector with itself and they're unit vectors. That means the sum on mu gets replaced by 2 because the answers don't depend on polarization. And so this integral then turns into 2 pi h bar here, the prefactor there. There's a 2 pi cubed in the denominator, which came from there. If I take this integral over k and go to polar coordinates, I get a 4 pi for the solid angles and then an integral from 0 to infinity of k squared dk. What's left of the integral? The sum on mu, as I said, turned into 2, so let me stick a 2 in there. And then what we have left is omega, which is, let's just write it as, I'll leave it as, let's write it as c times k. We need to do that. And that's it. That's what we get. And you can see already by looking at this that this integral is going to be infinite because it's basically the integral over all k, magnitude of k now of k cubed, which is going to go like k to the fourth. To give us something to work with, let's replace the upper limit of infinity by some capital K, which is a kind of a cutoff. Let's let K be equal to a cutoff here. We'll worry about what that is in a minute. But if you put this all together, here's what you get is you get h bar c divided by 2 pi, h bar ck, h bar c divided by 2 pi times capital K to the fourth. That's what you get. H bar c times capital K to the fourth. It had to go as the fourth power of this k. And so this then goes to infinity as a k goes to infinity, as the cutoff goes to infinity. All right. Now, so let me summarize it here. Is the vacuum expectation value of the square of the electric field at a point x is equal to h bar c over 2 pi times capital K to the fourth. Now, the question is, how do we understand this? And this goes to infinity. How do we understand this? We just, we're measuring the electric field in the vacuum. What does this mean physically? The average value of the electric field in the vacuum was 0. We thought that was good. But now it appears that the dispersion is infinite. And so that can only mean that individual measurements are infinite, that somehow average to 0 in some kind of weird mathematics. Aside from the worrying about the weird mathematics, there's the physics of it, because we know when we go and measure electric fields, we don't get an infinite answer. So how do we reconcile this with what happens physically? And the answer to this is that whenever you make a real physical measurement, let's say of an electric field, you do so with an instrument that has some finite size. In particular, if it's got some size like this, let's say it's got some linear dimension like this, let me call it L, like so. Then the instrument in effect averages the field over a spatial volume whose linear dimension is L. And that means that if the frequency of the field, or let's put it this way, if the wavelength of the field, lambda, the wavelength of a component of the field is much smaller than L, then you get a lot of small oscillations in there which average out to 0. In other words, an antenna of length L is not very good at picking up high frequency signals that have a wavelength much smaller than the size of the antenna. So the size of the instrument in effect provides the cutoff. And the cutoff capital K then is the order of 1 over lambda, which is of the order of 1 over L. That is to say the wavelength lambda is comparable to L here if you're speaking of the cutoff. And so what that means is this expectation value then for an instrument of real size, we can write it this way, is 2 pi times K. There's K to the fourth there. I'll take one number K out like this. There's also an H bar C there. Here, I didn't do this right. The 2 pi's in the denominator to bring this out here. There's an H bar C upstairs. Let me take one of the factors of K. The 2 pi in the denominator I'm going to ignore because this is just an order of magnitude estimate now. And then we have the K cubed left over, which is the same thing as 1 over L cubed, like this, as an order of magnitude. This is what we get. Now H bar CK, K was the cutoff in K space. If I write omega is equal to C times K, then this omega is an omega cutoff in frequency, just measuring in frequency units. So I get H bar omega cutoff here times divided by L cubed. And this is the average value of the electric field measured in the vacuum. We can call this the quantum RMS fluctuations of the electric field due to quantum mechanics on making measurements in the vacuum. All right. Now, so the question now, I think the obvious physical question now is this real? Are there really vacuum fluctuations of electric fields in a vacuum where there's no sources around anywhere? There's no light waves, no nothing. But if we go and measure an electric field, do we really get fluctuations like this? And the answer is yes, they are. They actually are real. And they have real effects. For example, they cause an electron to kind of jerk around in response to the fluctuating field. This causes modifications, for example, in atomic energy levels, which are observable. In fact, if we're talking about the hydrogen atom or other atoms as well, for that matter, the effect is called, guess what? The Lamb shift. This, in fact, is a physical explanation, one way of viewing it anyway, of the Lamb shift, which we talked about in somewhat qualitative terms last semester. In any case, the reality of these fluctuations appears in the measurable Lamb shift. Now, what about if we have I've been talking about a vacuum, but a vacuum that's say with no light waves in it. But suppose we do have light waves in it. Suppose we've got an antenna here or something, and it's broadcasting a signal, and we'd like to be able to detect the signal. So the signal has a certain E squared signal at any point in space, like any point where you want to make an observation. Let's say right here is an observation point. There's an E squared signal, and it's plausible that in order to detect the signal, in order for the signal to be detectable, we should require that E squared signal should be much greater than the E squared quantum fluctuations, which are due to the vacuum fluctuations. Well, in terms of describing the E squared signal, let's define N. Let's make a definition as N is the number of signal photons. I mean, this antenna is blasting out photons in all directions. Let's let N be the number of single photons per unit volume wherever you are. It diminishes, of course, the further away you move from the antenna. If so, the E squared signal, and I'll remind you that in the units we're using, which are Gaussian units, the energy density in space is E squared plus B squared over 8 pi. For a vacuum light wave, the electric and magnetic contributions are equal to one another, so there's a factor of 2. And as far as the 4 pi that's left, I'm going to ignore it because I'm just doing order of magnitude estimates. So the result is that E squared signal is as an order of magnitude is the energy density in the signal. So let's write this as N, which is the number of signal photons per unit volume, multiplied times H bar omega, which is the energy of an individual photon. We then require that this be much greater than E squared quantum, but E squared quantum is H bar omega cutoff. And let's suppose that our receiver here has an antenna whose length is L cubed, where whose length is L, where L is comparable to the wavelength. So I can write this as lambda cubed instead of L cubed here. So this gives us the cutoff for an antenna of length lambda. And combining these two conditions together, combining these two expressions together, you see you can cancel the h bar omega, and you end up with a condition that says that n lambda cubed is much greater than 1. And so this leads to the standard condition, which is quoted in the literature for the detectability of a signal, an electromagnetic signal. The requirement being that the signal strength should be greater than the background strength that you would see from quantum fluctuations. And the criterion is that the number of photons per cubic wavelength should be a large number. When the number gets down comparable to 1, then quantum effects become important. By the way, in blackbody radiation, one can talk about the number of photons per cubic wavelength at different frequencies. And if you're well below the frequency maximum in the low frequency regime, this condition holds very well. If you go to the high frequency regime down the ultraviolet tail, this condition does not hold. And out there, the number of photons per cubic wavelength is small. All right, anyway.
May I ask a quick question about the vacuum being Lorentz invariant?
Yeah, sure, go ahead.
Yeah, so hypothetically, if you measure the field squared value that's in some reference frame and you get that result that you got, and then there's another observer who's boosted like near the speed of light,
Yeah.
I would imagine that they see that the photons have way more energy, or like they're at least lamp contracted in some way, that the E squared will change.
No, it's trickier.
No,
No, it's trickier than that. The reason is that the energy density is just one component of the stress energy tensor, and there are other components as well giving you the pressure. And I didn't talk about measuring them. If you're in the vacuum, the stress energy tensor is diagonal. It's got an energy component and a pressure component, and the off diagonal elements are all zero. It's a simple diagonal matrix. But if you that matrix, that tensor, that stress energy tensor is Lorentz invariant, has the same form in all Lorentz frames.
Okay.
That's how you get out of it. Yeah. Okay. All right. Okay. So that's a bit then about the next topic, which was the vacuum fluctuations. Now my handy sheet here that gives me my list of topics filled now, and so let me pin it back up again. All right. The next topic I want to address is what's called helicity polarization vectors. And for that, we need a new pad of paper. Up to this point, enlarge it slightly. Let me refix it, which I think makes it look better anyway. Not so yellow. Up to this point, the polarization vectors have been an arbitrary pair of orthonormal vectors, that's to say orthogonal, spanning they're orthonormal vectors that span the plane perpendicular to k. So if I've got some k vector, we have I call it epsilon hat k1 and epsilon hat k2, like this. And that's all we've used up to this point, and we made no further assumptions about these polarization vectors except they span the plane perpendicular to k. Now, however, I'd like to introduce a particularly convenient set of polarization vectors that are called helicity polarization vectors. And I'll tell you about them now. It works like this. Let's suppose initially our k vector is in the z direction. So I've got x, y, and z like this, and z going this way. Then I'm going to set up a set of polarization vectors spanning the perpendicular plane, and here's what they are. There's an E1, which is equal to x hat plus iy hat over the square root of 2, and an E minus 1, which is equal to x hat minus iy hat over the square root of 2. And you see that these are what you'd otherwise call circular polarization vectors. But I'm going to put a sign convention on the upper one with a minus sign there. And if I do that, then these two vectors then become two vectors of what we call the spherical basis that we worked with last semester. In fact, there's also an E hat 0, which is in the Z hat direction, which forms an overall orthonormal triad. So this is the spherical basis. Now, it basically represents circular polarized. The E plus and minus 1 represents circularly polarized light. The plus 1 is a left circular polarization, and the minus 1 is right circular polarization. If I follow the conventions that are used in optics books, that's how it is. Now, suppose my k vector is not along the z direction, but some other out direction like that, pointing some direction like that. Let's give this polar angles theta and phi in the usual way in spherical coordinates. And allow me to define a rotation matrix I'll call R of k. Depends on k. And it has the property that it maps the z hat direction into the k hat direction. So R of k can be written this way. It can be written as R sub z of angle phi times R sub y of angle theta. Or if you like an Euler angle form, it's R of phi, theta, and 0, with the third Euler angle is 0. And you can easily check that this RK has the desired effect of rotating the z-axis into the k-axis. At first the y rotation brings the z-axis down in the xy plane, and the z rotation maps it out to its final orientation. We've kind of been through this kind of construction before. In any case, let me define R of k vector that way. R really depends only on the direction of k. I'm writing as R of k vector. All right, now having done that, let's define epsilon sub k mu is equal to R of k acting on E hat sub mu, where mu is equal to 0 and plus and minus 1. In other words, we take the spherical basis over here and we just rotate it by this R of k. Now what that's going to do is it's going to take the z hat and map it into the k hat direction. So that's the 0 index here, mu equals 0. That, in other words, is what we call the longitudinal polarization, along k. And as far as the other two, it'll map them into the plane perpendicular to k, because rotation matrices have the property of mapping orthonormal frames into other orthonormal frames. So it has to be that way. And if we do this, then we now have not only two polarization vectors, which are now indexed by mu equals plus and minus 1 instead of we just called them 1 and 2 before, but now I'll start calling them mu equals plus and minus 1. And I'll call these the helicity polarization vectors, with the additional benefit that we now have also a longitudinal polarization, which is the case mu equals 0 is the longitudinal polarization. Now, light waves don't have longitudinal polarization. They only have the two transverse ones, but it's convenient to use that language for talking about the third direction, k hat. Interestingly enough, it turns out that if the photon had a non-zero mass, then it would possess all three polarization states, including the longitudinal one. There's been a certain amount of interest. I'm not sure it's been at the top of the heap. A certain amount of interest lately that what are called longitudinal photons, which would exist, by the way, if the photon had a mass, that longitudinal photons might be the explanation for dark matter. And there's been estimates for how that could come about, and based on what we know about the mass of the photon and so on. The mass of the photon is normally assumed to be 0, and this is pretty integral to the standard model, but of course it's an experimental matter to test it. And experimentally, it's known that the mass of the photon has a very low upper limit. The experimental upper limit is quite small, but it's not 0, never can be. So it's still an open question. There might be a small photon mass. If there is, then longitudinal photons do exist. And the question is, what's the nature of them? And part of the answer to that is that they would interact only very weakly with real matter. They'd be like even worse than neutrinos in that respect. And so this is one reason why they're regarded as a possible candidate for dark matter. Anyway, I'm just mentioning this is some of the vagaries and ramifications of what you call longitudinal polarizations, or longitudinal photons. All right. In any case, standard light doesn't have them, but we get the vector there anyway, the mu equals 0 vector. Anyway, these are the polarization vectors, the so-called helicity polarizations. Now, the helicity polarization is convenient for discussions of the angular momentum of the electromagnetic field, and in particular the spin of the photon. And I want to say some things about that. We've already covered the energy of the photon. The energy, of course, was h bar omega, and the linear momentum of the photon was h bar k. Oops, h bar k. K has an arrow, the h bar doesn't. So energy and linear momentum, we've talked about that. But now what about the spin or angular momentum of the photon? You'll recall that we got both the energy and linear momentum of the photon by taking the classical expressions for the energy and linear momentum of the classical field and then quantizing them. We used basically Dirac quantization, reinterpreting classical observables as quantum observables. We had to worry about normal ordering, but the result was we got operators acting on the state space for the field, and these gave us definitions of energy and linear momentum for the field. And then we can talk about the corresponding quantities for eigenstates of energy and momentum, and this is what we got for individual photons. Now, if we do something similar for angular momentum, the story kind of goes like this. Let's call J the total angular momentum. J is not the current here, it's an angular momentum. Let's call J, let's first of all work at the classical level, okay? First of all, classically. Let's call J the total angular momentum of the electromagnetic field. There's a matter part which I'll skip because we're just talking about the free field here. The field part is this, it's 1 over 4 pi c, the integral over all space d cubed x, and then we have the position vector x, which is crossed into E cross B. It's x cross E cross B integrated over space. Now E cross B over 4 pi c is the momentum density in the field. So crossing that with x makes something that looks kind of like an R cross P, you see, density, and then we integrate that over space. So it's actually kind of a plausible formula. But you don't have to guess this formula. You can derive it from the Lagrangian for the electromagnetic field, which is invariant under rotations. And again, using Noether's theorem, one can derive in a systematic way the corresponding conserved quantity, and that's what this is. This is one of the conserved quantities for the free electromagnetic field. And those are actually important topics in electromagnetism. I don't know if they covered them in 209, but they're important because the energy, linear momentum, and angular momentum, in fact, are the only exactly conserved quantities which the field equations have. So they're important for that reason. Well, in any case, this gives us a J. Now, if we work in Coulomb gauge, it turns out this can be broken up into two terms, which we call L and S, and we call by names the orbital and spin contributions to the total angular momentum of the electromagnetic field. We use this language even at the classical level, even though it's not in classical E&M. It's not orbital and spin. But it's convenient language to use nonetheless. And the idea of it is this. I'll explain it as briefly as possible. Is that to get the conserved quantity, you need to study what happens to the field under rotations. The electromagnetic field is a vector field. You know, E and B are vectors, and the vector potential is a vector. And if you rotate it, if you study rotations, you not only rotate, you know, the observation point in effect, but you also rotate the value of the field. And so there's two aspects to the rotation, the observation point and the value of the field. Well, rotating the observation point gives you L, and rotating the value of the field, let's say the direction of the electric field, that gives you the S. If you were doing this with a scalar field, you wouldn't have any S part, you just have L. And that would just give you, you know, what we know already in quantum mechanics is scalar particles. That's the orbital angular momentum. But in any case, even at the classical level, this decomposition occurs, and that's the origin of these two terms. Now, these things can, the formulas then are the following. The L is equal to 1 over 4 pi c. It's a formula I won't justify, but here's what it is: integral over d cubed x. It's x crossed into the gradient of the vector potential A dotted into the electric field like that. Whereas the so-called spin is 1 over 4 pi c, the integral over space, d cubed x, of the electric field crossed into A. And this is only in Coulomb gauge where this works. So that's what I'm doing here, this decomposition. But in any case, this is what the decomposition is in Coulomb gauge. Now, I'm not going to talk about the orbital angular momentum of the field because it's too complicated. I want to just give you an overview, a general idea. I'll just talk about the spin. So this formula then is a contribution to the angular momentum of the classical field. But following what we've done earlier with energy and linear momentum, we can promote this into an operator acting in the quantum field. We do so by reinterpreting both E and A as operators, the quantum fields that we've been talking about a lot. Here's the Fourier series for them there. They're now written as operators. And we normal order them because we know we have to do that. And if we do this, this thing can be reinterpreted now as a spin operator for the field, for the quantized electromagnetic field. Moreover, plugging in the Fourier series for E and A, we can do the integrals and express this in terms of creation and annihilation operators. It's actually somewhat cleaner to do this, or it's easier to understand the answer anyway if I go back to box normalization and doing it. And I'll show you what the answer is. In the first place, the answer is not simple unless we use helicity polarization. So let's assume that it's helicity polarizations. If we do, it turns into this. It turns into a sum on, let's see, how explicit shall I be? I'll sum on K and mu. And then I hope I have enough room here. And then we have H bar times the direction K hat. And then what we have is mu itself. And then we have the creation operator, A dagger K mu, and the annihilation operator, A K mu. The product, of course, is a number operator. It's that. I could bring the H bar K outside of the mu sum. In fact, let me do that. Let me write this in a slightly different form. It's a sum on K, and then we've got H bar K hat. And then for the mu sum, let me write it out explicitly. For helicity polarization, mu is plus or minus 1. So what I get is with a plus 1, for the mu equals plus 1, I get a number operator here for K plus. And then the second term comes in with a minus sign because mu is minus 1. I get a number operator for K minus. And so this is the spin operator for the field using box normalization. And what this is telling you is that this field operator gives a contribution to the angular momentum of the quantized field, which is in the direction which these are now occupation number eigenbases that we're talking about here. So as the K value is defined, is that it's in the direction of propagation. It has a magnitude of H bar, and it's plus 1 for the plus 1 helicity state, and it's minus 1 for the minus 1 helicity state. This is interpreted by saying that what we're talking about here is the projection of the spin of the photon under the direction of motion of the photon, under the K vector direction. If you take a spin, we know this, if you take a spin of a massive particle, stuff we did last semester, and you project it onto an arbitrary direction, we usually make it the z direction, but that doesn't matter. You can project that in any direction you want. Then the values of the corresponding operator, the components of spin in any direction, run from minus s up to plus s, total of 2s plus 1 values. 2 for a spin a half particle, 3 for a spin 1 particle, and so on. Then the magnetic quantum number, gives how much the spin is. What we're finding here is we're in effect getting the projection of the spin onto the direction of motion. And in fact, if this were a massive particle, what we would find is 3 values. There'd be a longitudinal polarization in there as well with a value of 0 that would be contributing. But we don't have any longitudinal polarization states. We just have the transverse. And they give us a contribution to the spin, which is H bar if it's helicity 1, and minus H bar if it's helicity minus 1. What's going on here is that because of the masslessness of the photon, the longitudinal polarization is missing, so we only have 2 terms. But the fact that there's an H bar that appears, so you might naively say, oh, maybe this is a spin a half particle, it only has 2 states. No, because the magnitude is H bar, not H bar over 2. This is a spin 1 particle with a missing longitudinal polarization. That's the interpretation of this formula. Now, I'm glossing over a lot of details, but this is some of the ideas that lie behind this. So part of the conclusion of this, which I'm not delving into detail about it, but part of the conclusion of this is that the photon is a particle of spin 1, which, however, is missing one of the 3 velocity states by virtue of the fact that it's massless. All right. The next topic I want to address is the following, and maybe I just got enough time to get started on it. A striking feature of this formalism that we're developing is that we've got a way of talking about particles in quantum mechanics that does not involve wave functions, at least not in the usual sense, not what we're used to based on what we did last semester. Instead, what we've got is harmonic oscillators, occupation number bases, field operators, Fourier series for fields, and all kinds of stuff like that, that we don't have wave functions for particles. So the question then arises is, what is the relationship between this formalism for describing the quantum mechanics of particles and the one that we're used to, which involves wave functions? Or I could summarize the question more briefly by saying, what is the wave function of the photon? All right, let me make just a beginning on that question. Let's let E sub EM be the state space for the electromagnetic field. We can break the state space up into subspaces depending on the number of photons. The space that has 0 photons in it, and now I'll use continuum normalization. The space that has 0 photons in it is just the vacuum. That's all there is. It's a normalized, it's a one-dimensional space, which is normalized state spanning that space. What about 1 photon states? Well, to get a 1 photon state, and I'll do this over here on the right, let's write down the vacuum first of all. Then let's apply a creation operator, an A mu dagger of K, like this. Now, this isn't really a state in a physical sense because it isn't normalized. It's not normalizable. To create a normalizable state, we need to form linear combinations of this. So parameters are both mu and k. So let me introduce coefficients that depend on mu and k. Let me call them f. So f is some function of mu and k, a general complex function of mu and k. And then let's sum this on mu and let's integrate over k in order to form an arbitrary linear combination. And let's call this psi sub 1 here, like this. And the 1 means 1 photon. And the idea of this is that psi sub 1 is a general expression for a state belonging to the Ket space E sub EM containing a single photon. And you see it specified by this expansion set of expansion coefficients F mu of K. This, as it'll turn out, since I'm out of time tonight, I'll elaborate on that next Tuesday. This can be regarded as the wave function of the photon. And so and we can do something similar with 2 photon states and so on. I'll go into that more next time. But let me just say that what this amounts to is taking the state space for the electromagnetic field and decomposing it into a set of orthonormal subspaces. There's first of all E0 containing no photons at all. That's just the vacuum. There's then orthogonal to that is the space E1 containing 1 photon states. And then there's another space with 2 photon states and so on going all the way out to infinity. So the state space for the field involves subspaces containing different numbers of photons. And so in this space E sub EM, for example, it becomes possible to talk about linear combinations of states with different numbers of photons, something we couldn't do with wave function language describing it's in systems that have a fixed number of particles. Those are the only systems we've considered up to this time in this course. Now we have a variable number of particles. We can form linear combinations of states with different numbers of particles. We have operators that can change the number of particles. Indeed, that's what the creation and annihilation operators do. This is what happens when matter interacts with radiation. It either emits or absorbs radiation and causes transitions amongst these different subspaces, changing the number of photons. This is going to be the theme that we'll develop in the next couple of lectures. All right, so that's all for tonight. Are there any questions about this? Notice, by the way, that the wave function of the photon only applies to field states that lie inside that subspace E1. We can talk about other wave functions for E2 and so on, and I'll do that in the next lecture. But that so far, that's it only applies to that one subspace. Yeah. So, are there any questions about this?
I have a question about the dispersion of the electric field that we found.
Yeah, the E squared. Yes.
Yeah, I was wondering if you could also just get that from taking the energy density we had already calculated and then taking the zero temperature limit, if that would be
Well,
equivalent.
yes, absolutely. Yes, absolutely. In fact, that's kind of a hard way of doing it. I mentioned that as a matter of fact, because E squared is one of the terms in the energy density,
Right.
and it's actually its magnitude is the same as B squared for light waves. And we know that the energy density in the electromagnetic field, if we use if we didn't do normal ordering, we know the answer would be infinite. We get the infinite 0-point energy. Well, so in computing this expectation value that we're doing here, we're really reproducing all over again the calculation of the 0-point energy, except we're not doing normal ordering. Why aren't we doing that? Because we're not trying to find the energy of the ground state. We're trying to find the fluctuations. So no wonder the answer is once again infinite. It's like we got rid of the infinity in the Hamiltonian, but it pops up again when we compute the dispersion of the electric field. It didn't go away. Okay, any other questions? Those are good questions. Any other questions? Okay, then I'm going to stop screen share. And
I did just want to remind you that next week is spring break, so we don't actually have class next week.
yeah, thank you for reminding me of that. Yeah, so if I've been talking about seeing you next Tuesday, it's really seeing you next Tuesday plus 1 week.
Right, yeah. I figured. I just wanted to just double check.
Yeah, to make that clear. Yeah, so I'm gonna make the homework due a week later too, because there's no reason not to. I will hold office hours on Friday of next week though, in case you need to talk about anything. All right then, thank you for your attention, and I'll see you in a week and a half.